This is an example of how we can use the systems view to undertake a topic as large and as nebulous as sustainability. So we're going to talk about the minimum requirements for sustainability, and in particular, focusing on an example of a natural resource. What if you wanted to maintain a sustainable harvest? So this is just an ecological example. At the very end, I'll talk about something else, a human and economic example. But I just want to talk about just what's the minimum definition of sustainability and how using a systems approach can help. So first thing we would need to know is that the harvest can exceed the growth in any one year. And if you look at this as a stock and flow system, we have the resource, we have the growth of the input, and the harvest use is the output. And if the harvest exceeds the growth input, the resource is going to decline. And if the harvest use is less than the resource, then the growth input is greater, and you're going to get increase in resource. So for a sustainable use of this over a period of time, you really can't have harvest greater than input. Now we're going to be talking about sustainability and how in sustainability there's natural capital has a special value. And that's called the strong sustainability argument, that you can't replace physical or financial capital with, you can't replace ecological capital with physical or financial capital. So for example, you can't just say, we're going to use a sewage treatment plant or a marsh to clean up water and their equivalent. In the strong sustainability argument, the marsh would have other values related to biodiversity and ecosystem integrity that aren't represented by just having the sewage treatment plant. So this is one of the reasons why we do focus so much on having natural capital in the definition of sustainability. But again, in this example, we're just looking at a simple natural resource and a growth and harvest. Now, the first thing about biological processes, such as fish populations or the growth of trees or the growth of other organisms, is that more natural resource usually leads to more of that resource. So, for example, a healthy fish population leads to more fish. Now, if you get too many fish, the population will slow down. And if you have a forest that's crowded in trees, that population will slow down. But in general, a healthy population will have more growth. And this is what we call a positive feedback cycle. So when we have a high amount of natural resource that's very healthy, it actually has a positive feedback on the growth, and you get more natural resource produced. Now, if we harvest too much, that obviously decreases the natural resource. And that's just and thus it'll decrease the growth rate of that natural resource. But we can also decrease the growth rate by using bad harvesting techniques. So an example of this, like let's say we want to harvest trees and build drive bulldozers all over the soil and compaction and erosion. The process of harvesting not only takes natural resource away, but it makes conditions. These conditions are degraded, and those conditions would have been good for the growth of the tree. So bad harvest techniques can lead to degrading the conditions that are necessary for good growth. We see this in fisheries by taking the size of fish that is most reproductively active. You can take the same amount of fish, but just the mechanism by which you take the fish can degrade the resource. So we'd want to stay away from that, and we want to use harvesting techniques and approaches that don't degrade the growth characteristics of the natural resource. The other thing that we have to deal with when we're talking about a sustainable harvest is we're talking about here's the growth and the harvest, and what if those are all in balance, but then we have one bad year. And one bad year, you might think, well, that can't have much of an impact. But over here, it's just an example of what can happen if you start out and near the beginning of trying to grow things. You have one bad year, but you take the harvest as if everything was a good year. And every harvest after that is based on what you should get in a good year, based on scientific principles. But just because you like had this little blip at the beginning and we're underneath, the population you need to sustain itself, it eventually just decreases. So this is a very simplistic view, but if you imagine that you have variable conditions like drought, or maybe an occasional fire in a forest, or maybe sea conditions affecting fish populations. The variable conditions, you can have one really bad year and it'll really throw off your whole sustainable harvest plan, and you have to adapt to that. So in sustainable management plans, we really have to deal with the risk or the uncertainty of some of these bad conditions. Now again, this describes just the minimum condition. We might want to have much more from our community and our natural community and ecosystems than just barely meeting the minimum provision. We might want to have those populations thriving and producing biodiversity and being a place for recreation and aesthetic value. So this is just like the bare minimum conditions we need to meet, and the problem gets much more complex as we add all those other constraints. Now, one of the good things about using a systems view is that it opens up some of these questions. So for example, the question of sustainability and can we sustain wealth? Well, let's look at a population here of humans. There's births and there are deaths. And the birth rate, what if that's linked to the wealth per capita? More wealthy families actually have fewer children. Poorer families have more children. It's like a negative relationship here. Well, what happens in this, and we're going to study this when we talk about the demographic transition in ESM 102, is if we have a certain amount of economic growth, and that leads to wealth of the nation, but we have a population that's growing faster, there'll be, even though there's an increase in wealth, if the population growth outpaces that, there'll be a decrease in wealth per capita. Now, that's a pretty broad topic, and again, we'll be talking about that when we talk about the demographic transition. But just opening it up here and talking about here's population growth, here's economic growth, these are connected by a wealth per capita. This visual here really shows what are we talking about when we talk about wealth? Is wealth the ability to, the amount of resources you spend? Or is wealth something that's related to the amount of resources that you protect and allow to renew itself? So is wealth the money you have in the bank and that you spend every month? Or is wealth the amount of money you have and property you own that you're a good steward over and maintain the natural capital and sustainable growth? These are very broad questions, but we can focus on really what we're talking about by using sort of a systems diagram like this and focusing on particular topics. It doesn't help us answer the question. It just helps us frame it in a way that we can maybe draw some information. Now finally, one of the things that systems view does is help us open up the questions, identify our assumptions, and then if we do that, it might help us avoid unintended consequences. And again, one of the values of using many different tools to address problems is that the more tools you use in concert, the more chance you have of avoiding surprises and bad unintended consequences. So in the coming weeks, we're going to be talking about network view, we're going to be talking about game theory, and we're going to be talking about uncertainty, and all of these together help us frame the questions and look at it so we can avoid some of these bad consequences.